Okay, thanks for coming. I'm very happy to be talking to you about asymmetric top molecules. So as the day goes longer, the molecules get wackier. But I hope to convince you that these are really interesting targets for future laser cooling experiments. And I think one way to think about the way that we've been approaching all of the talks you've heard today is to think about a systematic increase in complexity or decrease in symmetry. So obviously, this whole conference is focused on the transition from atoms to molecules, where essentially we've taken a spherical object and reduced the spherical symmetry to cylindrical. And we have a moment of inertia that describes the molecules. That leads to a lot of the complexity that people have had to describe dealing with already today. And a lot of that's been handled really successfully, most notably, I think, with the optical tweezer experiments that have been conducted with CaOPh molecules, as well as other diatomic molecules. But what I want to talk about in my talk is what if we take this systematic descent further? So what if we think about eliminating cylindrical symmetry and talking about a symmetric top molecule where now, because of off-axis atoms, the molecule can rotate about its figure axis. And then after that, we'll take the step towards fully asymmetric top molecules. So I just want to recap some work that was done in the Doyle group about a year or two ago, where we attempted to laser cool calcium monomethoxide, CaOCH3. And this is already somewhat more complicated than even CaOH. First of all, the most obvious issue may be that this molecule has 12 vibrational modes. And even though it has favorable vibrational branching ratios, this is still a rapid increase in the number of vibrational modes compared to the 3 that were present in CaOH. The second feature, which is actually quite interesting, I think, is that because of the rotational motion of the hydrogen nuclei about the figure axis, we can label these rotational states by a quantum number called k, and the lowest two would be k equals 0, k equals 1. And these are actually formally tied to the nuclear spin statistics of the hydrogen atoms off of this molecule. So when we drive transitions, we actually see there's already an interesting coupling between the particular transition that we choose to drive and even the nuclear spin statistics that are active in these molecules. So with CaOCH3, there were essentially 2 nuclear spin isomers of CaOCH3 that we could laser cool. And by choosing the rotational state appropriately, either k equals 1 or k equals 0, we were able to address both of these. And just going really quickly through the experiment, we essentially took a buffer gas beam of calcium monomethoxide, passed it through a laser cooling region that consisted of a what would be familiar to many people in the audience as a typical Sisyphus cooling setup. And using just 3 lasers, we were able to see a really nice compression in the spatial distribution of this molecular beam, which, because the molecules are flying and expanding, corresponded to a decrease in temperature to just around the millikelvin or slightly below region. So what's really exciting about this is that we're seeing that the initial steps taken with symmetric top molecules, nonlinear molecules, are really paralleling what was done by pioneering work in molecules like strontium fluoride and Dave DeMille's group. So this is a really exciting step forward for increasing the complexity of molecules, but maintaining the ability to control them with lasers. So most of what I want to talk today is actually about the next step. What if we look at molecules that have 3 distinct moments of inertia, which would be classified as asymmetric top molecules? Can we still find molecules that have the right properties for control by lasers? Just to motivate a little bit why you might even want to do this in the first place, the thing that really, I think, excites me about this is that the unique geometries of molecules, if you allow yourself to use the full asymmetry of what nature provides us, are beneficial for pretty much any application that people in this room could care about. So, for example, any experiment that probes chiral molecules and any experiment that wants to probe a molecule with a torsional mode is necessarily going to have to work with an asymmetric top molecule. That's baked into those structures. And those particular motions, like a torsional mode of a methyl group around some other bond, is actually known to be highly sensitive to variations in fundamental constants. So molecules like this could be used for next generation experiments probing variations of proton to electron mass ratio or models that predict dark matter might lead to these fluctuations. In addition, even small triatomic molecules that are bent, like calcium hydrosulfide, have quite large dipole moments and very long-lived states that can be easily polarized, which means that they could be used in quantum simulation experiments with incredibly large couplings compared to what might be able to be achieved in CaF. And yet, because the ground state's very long-lived, you're not giving up any lifetime that might be present in a linear triatomic molecule in a bending mode, for example. And then lastly, these molecules are, of course, of interest for ultra-cold chemistry. If you imagine laser cooling a molecule with a carbon ring and then maybe dissociating the metal atom, you now have ultra-cold aromatic molecules, ultra-cold arenes, which could be used for interesting collision or chemistry experiments. And these molecules sort of cut across lines. So for example, a molecule like YBSH or SRSH might be interesting for an EDM experiment. And you see that there's a lot of interplay between the ways that these molecules could be used. So that's one of the things that's really exciting about these molecules. The other aspect is if we think specifically about organic molecules, these molecules that have something like a carbon ring would open this world up to the magic that organic chemists can do through substitution. So for example, precision substitution of a carbon nucleus that bears a nuclear spin, placing a metal atom at a specific location that might be sensitive to new physics, adding a methyl group with a torsional mode that also might be sensitive to new physics. All of these can be done, and you can buy the molecules that would be laser coolable with an aromatic structure like this appended on the end. So there's a lot of flexibility if we can control these molecules. The problem is, can we actually do that? So we know we want to form optical cycles and potentially use optical forces to control these molecules. But in a molecule with increased complexity, will we actually be able to repump the rotational and vibrational modes that need to be controlled? To get at this, so in collaboration with Tanya Zolovinsky's group and Ivan Kaziriev, who is a postdoc in her lab, we conducted some ab initio calculations systematically decreasing the symmetry of molecules that we looked at. So we looked at CaOH, CaCH3, CaNH2, and CaSH, which basically take you from C infinity V to C3V, C2V, and Cs in terms of the point group symmetries. And in all of these cases, we saw that the electronic orbitals are essentially unaffected by the asymmetry of the ligand. We're, of course, using this sort of tried and true recipe of building building molecules from electronegative ligands and alkaline earth atoms. But what this is showing is that this really works irregardless of the asymmetry of the ligand. And then with Claire Dickerson and Anastasia Alexandrova from UCLA, we saw that the same structure holds even for aromatic molecules that are bonded to a calcium atom. And you'll hear much more about these molecules later on in my talk and in the later talks today. So overall, with Ivan and Tanya, we were able to identify a really large and diverse class of molecules that we suspected would have the right structure to be controlled by lasers despite their asymmetry. We actually looked at molecules that had been produced in the lab before, so we could use semi-empirical methods that generally predict Frank-Condon factors very well. And for about 24 or 36 species, we were able to see that using simple normal mode analysis calculations, the predicted vibrational branching ratios all fall in the range between about the value that CaF has and the value of YBOH's dominant Frank-Condon factor. Both of YBOH and CaF have been laser cooled, so this is a good metric to see that many of these molecules are promising for these applications. Probably the most challenging aspect of asymmetric top molecules is that their rotational structure is extremely complicated, and is also the rotational strengths are correlated with the electronic structure. So the easiest way to see this is that when you drive an electronic transition from a ground state, which may have a essentially spherical electronic orbital distribution, to an excited state, the direction of the electronic orbitals determine which way the laser field can torque the molecule and cause it to begin to rotate. So bent molecules can have transition dipole moments that are directed along multiple principal axes of the molecule, which means that we actually need to be very cautious about which transitions we drive to make sure that the population that we're trying to cool doesn't just sort of diffuse out into many rotational states. But taking these effects into account, we were able to identify a closed rotational cycle for each type of electronic band, where essentially A, B, or C dictates whether the transition moment points along one of the principal axes of the molecule. So for any given type of electronic transition, we are able to find a closed rotational cycle that involves 2 or maybe 3 optical frequencies. Typically, the same laser could address all three of these frequencies using AOMs or EOMs. And depending on the asymmetry of the molecule, we may need to essentially take a linear combination of different sets of these transitions. But generally, the molecules that I showed a few slides ago can all be cooled with about 1 or possibly 2 lasers addressing the rotational closure for each vibrational state. So, okay, with that background underway, I'm going to tell you the story of 2 molecules that we've chosen to work with. The first one is CaNH2, which is essentially, to our mind, the simplest C2V asymmetric top that we could work with using our techniques. And then the larger molecule that I'll talk about is calcium phenoxide, or CaOPh. So what we wanted to do was look at the vibrational branching ratios in CaNH2. We used a fairly simple setup. We had a buffer gas cell where we flowed in helium buffer gas as well as ammonia, reacted that with calcium that was formed in our ablation plume, and then looked at the dispersed fluorescence, basically collected the fluorescence from the molecules, dispersed the wavelengths, and built up a map of the laser of the fluorescence intensity as a function of the fluorescence wavelength. So this is a direct measurement of the vibrational branching ratios. For the 2 lowest electronic bands of CaNH2, we saw that indeed these branching ratios are highly diagonal in the sense that the decay strongly favors not changing the vibrational state. Overall, for the A and the B state, the branching ratios are about 96 or 97%, and these agree extremely well with our calculations using normal mode analysis and the known geometries of CaNH2. So this is showing that not only are these transitions highly diagonal, but we actually understand essentially understand the vibrational branching ratios and what's giving these transitions strength. So using this information, we decided to focus on the beta-X transition and use existing high-resolution spectroscopy from Tim Simley and Peter Bernath's groups, and try to implement optical cycling of CaNH2. So the simplest thing to do is just take our buffer gas beam source, allow a beam of molecules to pass into an excitation beam, and if we drive the rotationally closed cycling transition that I showed on a previous slide, we see a molecular beam that passes through our experiment that has some intensity. When we drive both of the spin rotation components that need to be addressed in order to achieve the closed rotational cycle, we see that the fluorescent signal increases by about a factor of 7. Now, driving either one of these ground states, since they have about the same strength and about the same natural population, you might expect driving either of these individually would double the signal. So the large increase, much larger than a factor of 2, is saying that we really are scattering multiple photons from a single CaNH2 molecule, which is the first indication of optical cycling in an asymmetric top molecule. Now, we're limited right now by the interaction time, which is why we're not seeing the factor of about 20 that we expected. And we're also in the process of looking for a repumping laser to address the CaN stretching vibration, which would allow us to increase this to about 60 or 70 photons per molecule, which is a level at which we think we could start to attempt the 1D Sisyphus cooling that I showed for CaOCH3. So for the rest of the talk, I want to talk to you about this larger molecule, calcium phenoxide, that we've been working on in collaboration with a number of PIs from UCLA, Anastasia Alexandrova, Wes Campbell, Justin Karam, and Eric Hudson. You're going to hear more about the low-resolution spectroscopy, I believe, in Eric's talk. So all I'm going to say is that we made a very small modification to our system, where instead of flowing in ammonia, we flow in phenol vapor. We allow that to react with the calcium, and then we expected to be producing calcium monophenoxide. We collected the fluorescence that the molecular beam put out and imaged it onto a camera, again, using the same equipment. And after taking some extended scans, we were able to identify a few locations where we had signal that we suspected corresponded to CaOPh. So in particular, if we look at the dispersed fluorescence signal, the vibrational frequencies act as a fingerprint for the molecule and essentially give us high confidence that this spectrum is coming from calcium monophenoxide. And if we zoom in, we see that indeed not only are the frequencies matching what we expect, but generally speaking, the trend in the vibrational branching ratios is also close to what we expect. So this is really behaving like calcium phenoxide as we expected it to be. To get a better handle on the identity and the behavior of this molecule, we conducted high-resolution spectroscopy So this is in particular working with Sean Burcheski, who's a grad student in the Doyle group. And what we did was we formed the beam into a collimated molecular beam and excited the molecules with a CW dye laser. Just as a technical aside, we were actually able to increase the production of CaOPh by populating the calcium triplet P1 metastable state inside of the cell, which was just useful for increasing our signal to noise. And we investigated the two lowest transitions of the calcium phenoxide molecule, X to A and X to B. So after we were able to locate this spectrum at using this CW laser, you can see we obtained this really dense but really beautiful high-resolution spectrum. It is quite complicated because the rotational constants of a heavy molecule like this are only about 500 megahertz, which is quite a bit smaller than you may be used to with diatomic molecules. But using a number of different tools, we were able to investigate the spectrum and actually fit it quite accurately. So we used a pretty simple effective Hamiltonian model, and we're able to reproduce the lines in the spectrum with almost line-to-line accuracy. So you can see we're able to simulate the intensities and the positions of these lines quite well and identify the ground state and the excited state rotational levels involved in these transitions. The most important part about fitting the data in this way is that it gives us a set of molecular constants that we can use to interpret the molecule and gain confidence that we really do understand the structure of this molecule. So in particular, the rotational constants, which give information about the geometry, agree extremely well with the predictions from Claire's ab initio theories, telling us that the bond lengths are well understood and really confirming the nature of the molecule that we're observing as CaOPh. And the main other structural parameter that I want to point out is this spin rotation constant, which is related to what Jinjun talked about. We measured this in both the A and the B state, and it turns out using the sort of theory that was in Jinjun's talk, you can predict, for example, that if the A and the B state are predominantly interacting with each other, then the value of epsilon in the A and the B state should be equal but opposite in sign. And you can see that, so of course the prediction based on sort of simple perturbation theory predicts that these numbers are equal and opposite in sign. And the measurement agrees extremely well, not only in the opposite sign, but also in terms of magnitude, which confirms our picture that this A-B state complex is really coming from the sort of excited p orbital in the residing on the calcium atom. So for all intents and purposes, this very large molecule is acting remarkably like CaF or CaOH, where the same sort of relationships hold. And that's really giving us confidence that the isolated electron, the radical electron on the calcium, is behaving very similarly to how it does in a smaller molecule like CaOH. So to put this data to use for optical cycling and laser cooling, one way to think about this spectrum that we took is it consists of, I don't know, maybe 300 or 500 individual lines, only one of which corresponds to the rotational transition that we want to drive to implement laser cooling. So this spectrum, of course, comes from a distribution of molecules, and almost, I'm exaggerating a little bit, but essentially every line in this spectrum corresponds to a group of molecules in our beam that are in a different initial rotational state. What that means is that this one feature, which is the one that corresponds to the rotationally closed optical cycling line, that's a subset of the molecules that we can actually manipulate in our laser cooling experiments. So you can see that one price we pay for working with larger molecules is that many molecules are just not in the right state to be laser cooled. And later on today, I think Wes Campbell is going to talk about some ideas to improve the situation. But for right now, we're just going to work with this little snippet of molecules that happens to be in the correct initial state. So we tried to implement optical cycling. And what you're seeing here is, again, we took our buffer gas beam. We allowed it to form into sort of a skimmed or collimated molecular beam. And then we imaged the fluorescence from the molecules as they flew across about a 1-inch region in our setup. So what you're seeing on the bottom here is when we do not drive the rotationally closed line, when we drive a purposefully lossy transition, we see that the molecules, they fly into a laser beam which we have made a very sharp edge on the input. and they start to fluoresce, and that fluorescence decays as they fly across the screen to the right. That's because as the molecules fly across the screen and interact with the laser beam, they're being optically pumped into other rotational states, which do not continue to interact with our laser. If instead we drive the molecules on the rotationally closed line, you can see that this fluorescence persists for much longer across the imaging region. And the reason for this is because the molecules continue to act with the optical cycling laser as they optically cycle. And the molecules are more slowly lost into other states which cannot interact with that laser. So this is some initial indication of optical cycling in CaOPh, which is great. But there are some really big problems associated with the signal that we're seeing. The first is that the actual increase in signal that we see is maybe 10 or 20%. If we were really optically cycling to the extent that the vibrational branching ratios predict, that should be about 10 times larger. So for some reason, we're not scattering as many photons as we expect to. The other issue is that we can determine the scattering rate as the molecules interact with this laser beam based on the number of photons we collect and the interaction time of the molecules with the laser, which we know from the velocity of the molecules. And the scattering rate that we extract from this is something like 20 or 50 kilohertz, whereas in typical experiments with CaOH or CaF, this would be more like 1 megahertz. So the scattering rate is incredibly low, and the number of photons that we're getting is too small. And to be honest with you, we don't actually know why that is. So this is kind of an appeal for help from anybody who's interested. There are many mechanisms that we can think of as to what might interrupt the optical cycling. And despite our best efforts, we haven't actually been able to experimentally demonstrate that one of these is the active culprit. But just to give you a feel for the sorts of things that we think might be going on in these large molecules, one is actually that the ground state spin rotation splitting is incredibly small. We were not able to resolve it in that optical spectrum, which given our resolution means that it's probably smaller than 1 or 5 megahertz, sort of at the largest. And that could give rise to very slow remixing of dark states in the ground level, which in a molecule like CaF would be remixed much faster due to the 10 or 20 times larger spin rotation constant. Another issue is that calcium phenoxide has 30 vibrational modes in it. And the density of states grows incredibly rapidly as the energy goes up, which means that the bottom of the A and B electronic potentials is embedded in a very dense manifold of highly excited vibrational levels from X. And the number, because I think it's almost comical to say, is actually that there's something like 10 to the 14 states per wave number at the location of the bottom of the A state potential. So some very, very weak coupling to this very dense manifold could steal population from the optical cycle. And then the last issue could be something more mundane, perhaps, like 2-photon ionization out of the low vibrational levels of the A or the B state. But like I said, we don't actually have the explanation for what's going on. We would love to have help, especially theory support, investigating this, because it's a really challenging problem. But solving it might allow us to better implement optical cycling and eventually laser cooling of these large aromatic molecules. OK, so just to summarize briefly, what I tried to tell you about was our approach to decreasing the symmetry of molecules that can be laser cooled, starting by direct laser cooling of the symmetric top molecule CaOCH3, which I think has a really promising path forward. And then branching into some work on asymmetric top molecules, where we identified a large class with diagonal Frank-Condon factors. And then our initial work to implement optical cycling of 2 particular molecules, CaNH2 and calcium phenoxide, where I think there's very exciting progress to be made, but challenges that we're trying to solve right now. So just the very last thing, there were a huge number of people that contributed to the work that I talked about. It was a really large and interesting team. So of course, members of the Doyle group contributed to all of the work that I described at Harvard. We had a large number of collaborators from UCLA, as well as from Columbia, and Tim Steinley, who is based at Arizona State University. And then lastly, thank you for your time.
Okay, we have a real mystery here, so that many questions. one suggestion and one comment. So if it's IBR, then you can deuterate, and by this normally the rate for IBR should drop in your case, and this is an experiment which is easily done. And if you then see that the situation improves, then you know that you're fighting against IBR, I guess. And the other comment would be, you said in order to go for chirality, you have to lower the symmetry further. But of course, there are also molecules which are highly symmetric, but still chiral. So you can have the symmetric top molecules which are nevertheless chiral. So some of the complexity you can, of course, reduce.
Okay.
I think deuteration is a big mistake because the vibrational frequencies go down, so the density of states will go way up.
This is good for IBR because there is a gap rule which says the smaller the gap, the higher the IBR is. So this is the old wisdom of molecular spectroscopy. If you deuterate, those processes go down. So it's not that the density of states goes up, it's the CH stretch which is promoting the coupling, and then by deuterating it goes down. So it's a good decision, not a big mistake.
We have to talk about it.
Yeah.
But you agree,
Counterintuitive,
you agree something would happen.
Maybe make my molecule smaller. I don't know. That's not the way you want to go.
Yeah.
Other questions?
Which one of the hydrogens do you replace?
All and then you're safe.
Maybe you can have some questions. for
Because
the
it's
speaker.
also
Yeah. Okay, maybe some questions. Yeah.
Lovely talk, thank you. John asked me yesterday about collisions with Rydberg atoms. So I guess I'm wondering whether what you want is a kind of cold Rydberg gas just outside the buffer gas source that the molecules pass through, and that pushes all the population down to the rotational ground state, enhances the number of molecules that are relevant to it.
Yeah, I think I mean any method that cools the rotations more than the buffer gas cooling does would be great. So collisions is one option. I think Wes is possibly going to talk about an option using lasers, but somehow cooling that distribution. The rotational constants are small enough that we're really talking about basically millikelvin temperatures. But yeah, collisions with millikelvin Rydberg atoms would be viable.